Hello everyone. So welcome to IITN Gate classes. So today I'm going to discuss about a gas dynamics topic called stagnation properties. So in today's video, we will see about how exactly we can define a stagnation properties and what do we know about stagnation properties and what are the misconceptions we usually get when we define stagnation properties. So I'm Akshay. So I'm your faculty for this gas dynamics course. So let us jump into the problem. So we have a set of governing equations when it comes to fluid mechanics problems. So before we heading on to stagnation property definition, first we will look at the governing equations and some of the essential form of a governing equation. So we will derive it first from the noun governing equation form. So this is a continuity equation. So which is in integral form. So the more useful form for our discussion is a differential form. But how can we derive a differential form of a continuity equation from the known integral form of continuity equation? So it's quite straightforward. You see here, we have a temporal derivative of a volume integral of rho dv. So again, we have a closed surface integral of a rho v ds. So here you see I have a set of streamlines. Let us say I am actually fixing a volume of my interest. So all the streamlines are passing through this volume. So let us say it is an infinitesimally small volume with the volume V. So all the streamlines are passing through this one. So we have a control surfaces through which a streamline enters and like the flow enters and flow exits. So I can call them those control surfaces as inlet and outlet for this particular volume. So basically what we have is a volume is enclosed by a set of surfaces, control surfaces, say like surface 1, surface 2, surface 3, like that. We have a 6 different surfaces for a volume. What we have considered here, it's basically a rectangular volume we consider. It can be any random shape per se, but it is enclosed by a control surface. So this integral is all telling about the flux which is coming out or coming in through the control surfaces, which is enclosing the volume. It's a closed volume. So that is why. So we can apply a Gauss divergence theorem to this one, because it is a closed surface which is enclosing a volume. So we can apply a Gauss divergence theorem. So what happens is like this term simplifies to volume integral of this. For a volume integral, this closed loop is not essential, because volume is essentially a closed enclosed surface. So no need to show that it's a contour. So now from a Gauss divergence theorem, I can write a divergence of a rho v this ds is a vector, actually the vector representative of a area. It basically denotes in which direction the area is facing. So now, so that becomes a dv. So if I club this to already existing volume integral of rho dv, which is equal to 0. So now both of the integrals are integrated with respect to infinitesimally small volume dv. So what I can do is, like, I can club those two integrands together to write a single integral equation, dou by dou t of rho plus del dot rho v times dv equal to 0. So because this integral is giving me 0, if my finite volume of interest is not 0, that means my integrand should be 0. So which gives me the form of this equation to be d rho by dou t plus gradient of rho v, which is equal to 0. This is a differential form of continuity equation. So we can further simplify this equation to write it in total derivative form. So how can we do that? So we have dou rho by dou t plus a gradient of. So you have to note here, this is not just some constant times a velocity vector. This is a density field times a vector field of velocity. So we cannot simply take like del dot rho v as rho times del dot v. It is not correct. Most of the time people do this mistake. This is okay when we have an incompressible assumption with density being constant, but it need not be true in all the cases. We have to understand that this is a vector operator which is operating on a scalar field and a vector field. So we have to be careful over here. So we have to use a relation of a vector operator operating on a scalar multiplied with a vector. So for that one, so what it happens is dou rho by dou t times, so rho times del dot a vector field or the divergence of a vector plus vector dotted with a gradient of a scalar. This is the form we have. So this is split into in this form. So as we can see here, so we have taken the scalar out and we have a divergence of a vector plus a vector dot product with the gradient of a scalar. So gradient of a scalar is a vector. So we are essentially doing a dot product between two vectors. So now you see here, this should ring a bell. So if I have the first term and the third term together, this is the second term. The first term and third term will say as this is a total derivative, right? So I can write together as d rho by dt plus rho times del dot v is equal to 0. This is another form of a continuity equation. And very famous equations like people usually do to check the incompressibility of the flow field, they use a divergence of the velocity vector to be zero. If divergence of velocity vector is zero, they say that the flow field is incompressible because the density is constant. So it has no, you see here, it has no temporal variation as well as it has no gradient because a gradient of a constant is zero. So it is not varying either in space, not in time. So these two term become zero, and only term which is left is in this equation, that is rho times del dot v, which is equal to zero, and that basically says us, because rho is constant, so to hold that condition, so divergence of vector has to be zero in incompressible limits. But it is not necessary that if the divergence of vector is zero, my flow field is always incompressible. It is not necessarily be true, but it is a very important condition when we define the potential flows, because potential flow either can be defined in pure incompressible flows and irrotational flows, as well as irrotational compressible flows also. We can use the divergence. All we have to satisfy is the velocity vector is a divergence free, or I can write the velocity vector as a gradient of some potential. So if I can write that one, I can use the potential equations even for a compressible flow. What does this indicates is like my potential flow is in the sense my velocity vector is conservative. So that is just for a thought. But all we are interested here is like the form of a continuity equation. This is the one in differential form. The other differential form is this one. This is very helpful in our other derivations when we go on to define the stagnation properties. Okay, so now similarly we have a momentum equation. Momentum equation is a little trickier in terms of obtaining in differential form. Again, we have a volume integral, we have a closed surface integral, we have a closed surface integral of a pressure, and a volume integral of a force field. So it can be either friction or a gravitational force kind of thing, or any force vector. F is a force vector here, where ds is a area vector and v is a velocity vector. So all the letters which are in the bold, that represents the vector field, and letters which are not in bold, that they represent a scalar field. So you just see the way I am saying, it's a field. It is I am not saying it's just density. I am not just saying it's pressure. It can be a field. It can vary as a function of time as well as space. So that is why it's a field, right? So this one is slightly straightforward, the pressure one, because this one we can use. I cannot use a Gauss divergence theorem. Instead, I can use a corollary, like that means the special form of a Gaussian theorem that relates a scalar field. So I can write gradient theorem. So using gradient theorem, I can write this particular part as volume integral of gradient of a pressure field times dV. Fine. So this is straightforward. But here it is quite difficult, because we have a vector field. So I cannot use a divergence field straight away. So for that one, what I'm going to do is like, I'm going to split this into individual components. That means surface integral of rho v dot ds u plus a surface integral of rho v dot ds times v. So my velocity vector is basically having three components. W ijk. Yeah. So I have three components of velocity u, v, w. So I'm splitting in terms of that one, plus a surface integral of rho v ds times w. So now this is a scalar quantity, so I can bring into rho uv form. So that is nothing but I'm as a representative case, I'm taking only the first term. So that is a surface integral of rho u v dotted with area vector, right? So for this one, I can apply a Gauss divergence theorem because this is now straightforward. So if I apply a Gauss divergence theorem to this term, volume integral of divergence of rho u v times dv. So similarly, I can apply a Gauss divergence theorem to the second uh, component and the third component of the vector. So now what happens is, you see the difference here. The entire momentum equation, it's a vector integral equation because it has a components. It's when you do the integration, you should end up in three terms. So say like some xi yj plus zk form. So the result is a vector. So this is a vector integral equation. So now we are doing it in a component based analysis, so that like we will be splitting the vector into three respective components, and we are applying the Gauss divergence theorem to each one. So here we applied a gradient form of a Gaussian theorem. So again, gradient of a pressure field, gradient of a scalar is going to be vector. So it again has three components, namely dou p by dou xi plus dou p by dou y j plus dou p by dou z k. So it is again a three components. So if I split it into a component wise, what I can do is like I can write like this. So I don't write three integrals. I'm just denoting it as a volume integral. It is dou by dou t of rho u plus volume integral of divergence of rho u v similarly, which is equal to minus volume integral of dou p by dou x dv plus volume integral of rho fx. So f is a vector, so in the x direction it is just fx, the component fx dv. So basically what I'm writing is f is a vector, so I can write in terms of fx comma fy comma fz. So three component of the vector. So in x direction, this is the only thing. So all of them are integrated with respect to volume. So I can take the volume integral as a common parameter. I can dump all the integrand into one single expression, dou by dou t of rho u plus divergence of rho u velocity vector plus dou p by dou x minus rho fx times v equal to 0. So now again similar condition. So the integrand has to be 0. So that leaves me rho u plus divergence of rho u velocity vector equal to minus dou p by dou x plus rho fx. So this is a momentum equation in differential form. Again, we can go on and show that in a total derivative form. So for that, again, I have rho u. Rho u is two scalar fields, whereas v is a vector field. So it is a scalar multiplied with a vector. So what I am going to do is like, I will club rho and v together and u as a separate vector field. So that means u times divergence of rho v plus rho v dotted with a gradient of u. And again, I have the term dou by dou t of rho u. So if I split that one, so that becomes rho times dou u by dou t plus u times d rho by dt. So if I take u common in this term and this term, so that becomes u times d rho by dt plus divergence of rho v. And surprisingly, this is nothing but our continuity equation. So from continuity equation, we saw that one dou rho by dou t plus divergence of density times velocity vector is going to be 0. So this entire term, I can treat it to be 0 because the continuity equation says us this is conserved. So this can be 0. So I have rho v gradient of a u component of velocity equal to minus dou p by dou x plus rho fx, and I have one more term over here, that is rho times dou u by dou t. So we left with rho dou u by dou t, rho v times v dotted with a gradient of velocity component in x direction, and dou p by dou x, rho fx. So if I write those terms together, that is rho dou u by dou t plus rho v dotted with a gradient of velocity in x direction minus dou p by dou x plus rho fx. So what I can do is like, I can take rho common. So if I take rho common, that gives me dou u by dou t plus v dot grad u, which is equal to minus dou p by dou x plus rho fx. So this means this is again a total derivative of a scalar, that is a component of velocity in x direction. So I can write d du by dt, the total derivative, equal to minus dou p by dou x plus rho fx. So this is a well-known momentum conservation in u direction. Similarly, I can write it for other component of velocity, that leaves me dv by dt equal to minus dou p by dou y plus rho fy, and rho dw by dt equal to minus dou p by dou z plus rho fz. So this is other two components of velocity, like momentum equations corresponding to other two components of velocity. So this is x momentum, and this is y momentum, this is z momentum. Right? So this is a momentum equation which can be converted to like from integral form to a differential form. And if I look at my governing equation, that is one more governing equation we can have is energy equation. Again, this is a scalar result. So the integral after integration, we will end up with the scalar, because we can see here this is vector dotted with vector, so it essentially yields a scalar. So the end result is a scalar over here. So it is straightforward to apply a Gauss theorem, Gauss divergence theorem. So the surface integral, this one will lead to a volume integral of a divergence of the pressure field times the velocity vector, the divergence. So dV. Similarly, this part, if I apply the Gauss divergence theorem, that is a volume integral of divergence of rho times E plus V square by 2. These two are the scalar fields and the vector velocity vector V dV. So if I take a volume integral common, so that again gives me the volume integral common dou by dou T of rho times E plus V square by 2 plus I have a divergence of this one, divergence of rho times E plus V square by 2 times a velocity vector minus rho q dot plus divergence of pressure field times the velocity vector minus rho times force vector times the velocity vector, the dot product, whole is integrated with respect to infinitesimal volume V equal to 0. So again, integrand has to be 0 to satisfy this equation. That leaves me dou by dou T of rho times E plus V square by 2 plus divergence of rho E plus V square by 2 times a velocity vector equal to rho q dot minus divergence of pressure times velocity plus rho times f dot velocity vector. This is my energy equation in differential form. Again, I can go on and show that in the total differential total derivative form. That means I can club E times E plus V square by 2 as one scalar field and velocity vector as other scalar field. So yeah, what I can do is like this term alone I can write I can again club rho and V together. So that is rho velocity vector dotted with a gradient of E plus V square by 2 plus E plus V square by 2 times divergence of rho V equal to rho Q dot minus gradient of divergence of PV plus rho times F dot V equal to, so again this one I can write in terms of rho times dou by dou t of e plus v square by 2 plus e plus v square by 2 times dou rho by dou t. So if I take e plus v square by 2 common from here and here, so that gives me e plus v square by 2 common, again dou rho by dou t plus divergence of rho v. Again, surprise, surprise, this is our continuity equation. So this term goes to 0. We left with density times v dot gradient of e plus v square by 2. Again, the one more term over here we have is density times dou by dou t of e plus v square by 2 is equal to the right hand term rho q dot minus divergence of pressure times velocity plus density times f dot v. So now if I take the density field common, rho common, so that leaves me dou by dou t of e plus v square by 2 plus v dot grad of e plus v square by 2 equal to RHS. So this is nothing but total derivative. So thus that brings me the form rho times d by dt of e plus v square by 2 equal to rho q dot minus divergence of pressure times velocity plus rho f dot v. So this is the form we will get as a differential form of energy equation. So this form of energy equation is a very important for us to define a stagnation properties. So let us move on to define a stagnation enthalpy then. So what I'm going to do is like to define a stagnation enthalpy, I will assume flow to be adiabatic. Adiabatic. And again, I assume there is no friction and no body force. Am I assuming it as steady? No, I am not assuming it as steady as of now. We will see it. All I am assuming is adiabatic. That means Q dot is 0. There is no heat transfer. I am assuming there is no friction and no body force. That gives me the force vector F to be 0. So I left with my energy equation rho times d by dt of e plus v square by 2 equal to minus gradient of PV, right? So this can again be written in terms of P times gradient of velocity vector plus velocity vector dotted with gradient of P. So it's sorry, P times divergence of velocity vector and velocity vector dotted with gradient of P. I can write like this term alone. Okay. Or if I have this term, I can write equivalently as gradient of PV. Okay. So now I am going to define one more term, that is rho times d by dt of P by rho. That is equal to rho times U by V form. So that gives me rho into dP by dt minus P into d rho by dt. So if I take this rho inside, so this gives me dp by dt minus p by rho times d rho by dt, right? That is nothing but rho d by dt of p by rho, right? So now I have continuity equation. This gives me d rho by dt plus density field times divergence of velocity equal to 0. This is the continuity equation of the other form we discussed. So now I have d rho by dt in this equation, and I can substitute this d rho by dt to here. That gives me rho times d by dt of p by rho equal to dp by dt minus p by rho times minus rho divergence of velocity. So minus of minus, it's plus, and rho get cancels. So I left with dp by dt plus p times del dot v. Okay, it's a straightforward. This is nothing but the left hand side is rho times d by dt p by rho. Right? So now dp by dt, that's the total derivative. So let it be there. Rho d by dt of p by rho equal to dp by dt plus I have the scalar field, the scalar pressure field times divergence of velocity vector, right? So now dp by dt, I can write it in terms of temporal derivative plus convective derivative, that is v dot grad p, and I already have the other term, that is p times divergence of velocity vector equal to the left hand side rho d by dt of p by rho. So again, this is nothing but these two terms, nothing but a divergence of a scalar times a velocity vector, right? This is essentially same. So I can write this to be equal to dou p by dou t plus a divergence of pressure times a velocity vector. That is equal to the left hand side rho d by dt of p by rho. And again, let me call this as equation 2, and I have my equation 1, that is nothing but my energy equation itself. This is my energy equation. So if I add the energy equation 1 and 2 together, that is nothing but rho times d by dt of, so I'm just adding equation 1 plus equation 2, d by dt of e plus v square by 2 plus rho times d by dt of p by rho, which is equal to minus divergence of pressure field times the velocity vector plus dou p by dou t, that is a temporal derivative, plus the divergence of pressure field times the velocity vector. So this term and this term get cancels. So all I left with. So this is again rho I can take common, and both of them are differentiated with respect to t. This is total derivative of two separate variable fields. So I can club them together to write rho times d by dt of E plus P by rho plus V square by 2 equal to dou P by dou T. Means we know from our basic understanding of thermodynamics, that is enthalpy is nothing but H plus P by rho, or it is equivalently H E plus PV, right? PV. So V is a specific volume, so it is nothing but 1 by rho. So I can write it E plus P by rho as H. So that is nothing but I have rho times d by dt of H plus V square by 2 equal to dou P by dou T. This is a very important step over here. You see, unless and until I have a steady flow field, I cannot define my stagnation properties, because this particular equation dou P by dou T, this is coming from unsteadiness in the flow. So it's an unsteady flow field. Then I cannot define my define the stagnation properties at that point, as long as the flow is unsteady. So if I take an assumption of steady, flow, then this temporal derivative vanishes. That gives me rho times d by dt of H plus V square by 2 is equal to 0. Now you see a differentiation of something which is yielding as a 0. That means the term which is inside the differential equation, or the which is differentiated, has to be constant. So that means H plus V square by 2 is equal to constant. So we define this constant as a stagnation enthalpy H naught. So for a steady inviscid adiabatic, and adiabatic flow field, we have rho dH naught by dt equal to 0. This is the idea of stagnation enthalpy. So where H naught is my stagnation enthalpy. So when I want to define a stagnation property such as stagnation enthalpy, you have to start your definition from a steady inviscid adiabatic flow. When it comes to rest, then the enthalpy which it attains is a stagnation enthalpy. So that is the full definition for a stagnation enthalpy. So we can go on and define for stagnation temperature. That is, if the gas is calorically perfect, then I can write H is equal to CPT, or H naught is equal to CPT naught, with Cp is constant. So in this case, my T naught is equal to constant in this flow field. For steady adiabatic inviscid flow, T naught is constant given that it is calorically perfect gas. So this is my stagnation and stagnation temperature. And my entire flow field can have a same stagnation temperature, given that all the streamlines originate from an uniform flow field. This is again very important condition. So if all the streamlines are originating from an uniform flow field, then only I can say the entire flow field has the same stagnation temperature. If they are originating from a different sources with a different streamlines having different stagnation properties, that means my flow field is having a different stagnation properties along a different streamlines, because like we should not get confused with this one. So this is what we defined so far. Till this point, it is considering a single streamline. We are imposing another condition of a uniform flow field, or the streamlines are originating from the uniform flow field. When I impose this particular condition, then I can say T naught is constant everywhere. So this is very important. And now I defined a stagnation properties for a flow field, but it is not necessary that the flow field has to be adiabatic flow field to define a stagnation temperature. It is a defined quantity. It is not like something which exists like that. It is a definition. So we can define a stagnation property to any kind of flow field. Say if it is isothermal flow field, or if it is isobaric flow field or isochoric flow field, it doesn't matter. We can define a quantity. But if I want to measure a temperature which is a stagnant, that means the flow has to come to rest adiabatically in an inviscid and a steady manner. So this is very important point to note down. So based on these definitions, we can define a different flow field. Say for a non-adiabatic flow field, if I measure at point 1, T01 as my stagnation temperature, and if I measure at some other point on the streamline, T02, and if a T01 and T02 are not equal, then it is non-adiabatic flow field. Similarly, if H02 and H01, given that if it is calorically perfect gas, so T02 and T01 is the better measure to do that. If it is not a calorically perfect gas, then we have to compare with a stagnation enthalpies rather than the stagnation temperature. If the flow field is said to be adiabatic at any 2 points on the streamline, my stagnation temperature or the stagnation enthalpies has to be constant. So they are same. And we can also define a stagnation pressure or stagnation densities for say, then I have to assume one more assumption, that is reversible as well as adiabatic. What we derived so far in our stagnation enthalpy definition is considering just adiabatic. We didn't consider whether it is reversible or irreversible. We took that as an irreversible process and we started off with. So it is fine to define a stagnation enthalpy for an irreversible adiabatic process, but to define a stagnation pressure or stagnation density, it has to be a reversible and adiabatic. That means isentropic flow. For a non-isentropic flow, if my stagnation pressure and stagnation densities are not equal between any 2 points on the streamline, then the flow field is said to be non-isentropic. And note that adiabatic flow field can be a non-isentropic flow field, but all non-isentropic flow field cannot be adiabatic flow field. Adiabatic flow field is an example for non-isentropic flow field, But all non-isentropic flow fields are not the example for adiabatic flow field. It's also important. And for isentropic flow field, it is straightforward. Both all three variables like P naught, T naught, and rho naught has to be constant in isentropic flow field. So because adiabatic flow field itself gives this condition T naught 2 is equal to T naught 1, and isentropic flow condition gives two more part, that is P naught and rho naught has to be constant. Okay, this is a point I wanted to discuss for this video, that is a stagnation properties. How do we define a stagnation properties, and what are the misconceptions we have? The main misconceptions we have is we always define stagnation temperature or something which the properties are something which when the flow comes to rest adiabatically or isentropically. That is not the full definition. You have to start with it is a steady, inviscid, no body forces, and adiabatic flow field. In an adiabatic flow field, if the flow comes to rest, then we can define that particular quantity as a stagnation temperature, a stagnation enthalpy. To define a stagnation temperature, you have to impose one more condition, that is in flow field of a calorically perfect gas. That is one more important term. Similarly, if you want to define a stagnation pressure or stagnation densities, then you have to start off with in a steady, inviscid, reversible adiabatic flow field for a calorically perfect gas. When the flow comes to rest, then the pressure what it experiences is a stagnation pressure, or the density what the fluid experiences is a stagnation density. And one more important thing I wanted to make is stagnation properties can be a defined quantities. It is need not be a quantities in the flow, but hypothetically, if the flow field comes to rest in following all the assumptions what we told, hypothetically, if flow comes to rest from that particular point of the from the flow, then I can define that particular quantity as a stagnation property. Say I have some streamline over here, I have some point, say some point A, and I have some pressure, density, and temperature, that is thermodynamic state of a fluid particle at this point, and I don't know whether it is coming to rest in adiabatic manner or isentropic manner, but if I define such that my flow is coming to rest from this pressure, density, and temperature, if it is coming to rest to velocity equal to 0, so I have some velocity v over here at this point, and it is coming to rest in an isentropic nature in a steady flow field with no friction and no body force, then the whatever the state it attains, P naught, T naught, and rho naught, those are a stagnation properties for a fluid element at point A, right? So this can be a defined quantities. This is important. Okay, so now we understood how we define a stagnation properties. Similarly, we can also define one more definition or defined quantities, that is called a characteristics properties. Say I have a subsonic flow field, and if I accelerate the flow field to a sonic condition, accelerate the flow field to sonic condition in an adiabatic process, then the temperature, so like here I have some temperature T, and the temperature what it experiences after acceleration is T star denoted by T star, that is called a characteristic temperature. Similarly, I can have other way to define characteristic temperature, that is in a supersonic flow field with a temperature T. If I decelerate the flow field in an adiabatic process, and the temperature what it experiences is a characteristic temperature. That is again a defined quantity. So hypothetically, a subsonic flow is brought to rest adiabatically, brought to a sonic condition adiabatically, or a supersonic flow is brought to a sonic condition adiabatically, then that particular quantity is defined as a characteristic properties, or sometimes denoted as star properties, right? So this plays a very important role when we derive a relationship for normal shock waves, like the property change across the normal shock waves and all. Then we need to define this characteristic temperature as well as characteristic Mach numbers and all. I am not defined my Mach number as of now, so I am not going to introduce you to the definition of characteristics Mach number right away. Okay, and most of the time people will have a confusion, that people make a mistake that they think m star is equal to 1. This is not true. This is not true. M is equal to 1 at a sonic condition. That doesn't mean my characteristic Mach number is 1. Say, like when I define my characteristic Mach number for a given Mach number m, it is not necessary that it is 1, because my m is different and all it is a defined quantities. If from this m, if I go to a sonic condition, then I have this Mach number is defined for some temperature T, and this is going to T star. So if I define to this one, so then this Mach number can be different. So that is why we have to understand that characteristic Mach number is not same as a throat Mach number conditions or whatever we see. So that is that is not exactly m is equal to 1 condition. This is not the condition when we say it's a characteristic Mach number. So when we define this one, we need to understand the idea of characteristic properties, similar to like how we define a stagnation properties. There we brought a flow to rest, but in this case we are bringing the flow to a sonic condition in an adiabatic process. Important. So again, I have to see here, in all due respects, the stagnation properties say T naught will always be higher than a static temperature. But the characteristic temperature, it need not be always greater than the static temperature at the flow field, because if I am referring to a subsonic flow field, then T star is greater than T for subsonic, whereas T star is less than T for supersonic, because in one case we are accelerating the flow, in other case we are decelerating the flow, and it can be vice versa. So it is always important. Oh, sorry, you see, like this is less for a subsonic flow, whereas it is greater for supersonic, because we are converting some of the dynamic energy to a dynamic temperature into this temperature, so it goes to higher values in supersonic. Yes. Okay, so this is again one more properties which we can define similar to stagnation property. Okay, let us take an example problem. So an ideal gas in a reservoir has a specific stagnation enthalpy of H naught. The gas is isentropically expanded to a new stagnation enthalpy of H naught by 2 and velocity v. The flow is one dimensional and steady, then the value of u square by H naught is equal to what? Technically, they shouldn't have given like stagnation enthalpy of H naught by 2 and velocity u, because when I say stagnation enthalpy, that means it is coming to rest. So, but it's okay to solve this problem. So say we have a reservoir which has H naught with a velocity 0. So this entire fluid, whatever it is having, it is at a stagnation enthalpy, and the new state is it goes to H naught by 2 and a velocity u. So now you see here, for assumption of a steady inviscid and adiabatic flow field, if the flow comes to H naught by 2 in this manner, so then what happens? I have H naught is equal to constant. So that means H naught is equal to H naught by 2 plus u square by 2. The new state, that is H plus u square by 2. The H is nothing but H naught by 2 as per the condition in the condition given in the problem. So that means I have u square by 2 is equal to H naught minus H naught by 2, or I have H naught by 2 is equal to u square by 2. So 2 get cancels. I have u square by H naught is equal to 1. That is asked in the problem. So the answer for this particular problem is 1. Very simple problem. So let us take one more example based on a stagnation properties. Consider a 1D adiabatic inviscid compressible flow. The moment when they say 1D, that means all the streamlines are originating from a uniform flow field. That is why they are calling it as 1D. So, and all the streamlines are having the same stagnation properties. So now, inviscid compressible flow of air with properties of air given to be R is equal to 287 joules per kg Kelvin, and the specific heat at constant volume is 718 joules per kg Kelvin. This is a gas constant, this is a CV. Through a duct of constant cross-sectional area, the area of the cross-section is given for a constant area duct. If the volumetric flow rate is nothing but Q is nothing but area into velocity, that is a volumetric flow rate. So how much of a flux which is going out of a given area, that is a volumetric flow rate, and stagnation temperature is 580 Kelvin. Then the air temperature inside the duct, they are asking the static temperature of the air within the duct if the stagnation temperature is known in that particular flow field, right? So now we will solve this particular problem. What they have given, I have a constant area duct where flow is going, right? So now they are given area is equal to 1 meter per square, and they are given a T naught is 580.05 Kelvin, right? That is what given in the problem, 580.05. Yes. So now I know that for a calorically perfect gas, T naught is equal to constant. So that means, or I have H naught is equal to constant, that is nothing but H plus V square by 2, which is also equal to Cp T naught times Cp T plus V square by 2. If I take Cp common, that becomes T naught plus T plus V square divided by 2 Cp. Right? So from here, I know what is T naught. I know what is Cp. How I can calculate Cp? Cp is equal to gamma R divided by gamma minus 1. That is one way. Or I have Cp minus Cv, which is equal to R. And Cv is given, R is given. If I have to calculate Cp, that is nothing but R plus Cv. So that is given to be 287 plus 718. That is given in the problem. 718. So if I add those together, I will get Cp. Cp is calculated. That is as a unit of joules per kg Kelvin. Right? So now what is V? So V can be calculated from volume flow rate information, that is A times V, or V is nothing but Q divided by A. So Q is given to be 680 and A is given to be 1 meter per square, 1 meter square. So that gives me 680 meter per second for velocity V. So now T is nothing but T naught minus V square divided by 2 Cp, or T is coming out to be 350 Kelvin. So if I calculate for T naught, T, the static temperature, so that comes out to be 350 Kelvin. Okay, so this ends up our discussion on stagnation properties. I hope you guys enjoyed this session, and for more information, you can contact on IITN Gate classes through a call or through inquiry on email, or you can also visit us on IITN Gate classes website. Okay, and importantly, the new batch for GATE 2023, that is for a crash course for GATE 2023 preparation, is starting from 1st of November. You guys can register, it is open. Okay, thank you all. To watch, subscribe, and share it to the peers, whoever interested to learn these gas dynamics concepts. Okay, then we will see you in our next session, so or the next video, where we will discuss on some other topics from gas dynamics. Okay, see you, take care, bye bye.